Determine the sum to infinity of the following infinite series. Let us begin. So we're going to name this infinite series as S infinity. So this represents the sum to infinite terms. This is going to be equals to, so here we have the first term given by 1 squared over 2. Then we have the next term 3 squared over 2 squared. Followed by the next term we have 5 squared over 2 cubed. Then we have 7 squared over 2 raised to the power of 4. Now this is an infinite series. Now this series is neither an arithmetic series nor a geometric series. That's because it does not have a fixed common difference, and also it does not have any fixed common ratio. So there's a possibility that it could be an arithmetico-geometric series, but that is also not the case. Suppose we consider only the numerator part of each of the terms. So from the first term we consider 1 squared, followed by 3 squared, then we have 5 squared, 7 squared, and the rest of the terms. Now clearly these terms are not forming an arithmetic progression because there is no fixed common difference here. However, if we consider from the first term 1/2, from the second term we have 1 over 2 squared, from the third term we have 1 over 2 cubed, then we have 1 over 2 raised to the power of 4. So these terms are going to be in geometric progression. So they are forming a geometric progression with the common ratio r equals to 1 over 2. So what we will do, we will take this common ratio. So let's name this infinite series as number 1, and we're going to multiply each terms with 1 over 2. That's going to give us 1/2 multiplied to sum of the infinite terms. This will be equals to, so let's take the first term 1 squared over 2, but when we multiply 1/2 to it, we're going to get 1 squared over 2 squared, but we're going to write it below the second term of number 1. So that means we have 1 squared over 2 squared. Added to, taking the second term 3 squared over 2 squared, multiplying with 1/2 gives us 3 squared divided by 2 cubed. Added to, now we have 5 squared over 2 cubed multiplied to 1/2 gives us 5 squared divided by 2 raised to the power of 4 plus the remaining terms. So this is going to be number 2. Now what we'll do, we will subtract 2 from 1. On the left hand side, so we have 1/2 of sum up to infinite terms. This will be equals to the first term 1 squared over 2 added to, now what we'll do, we'll take 3 squared over 2 squared, and from here subtract 1 squared over 2 squared. So that's going to give us a 3 squared, that's 9. 9 minus 1, that's going to be 8. So we have 8 over 2 squared. Added to, next we have 5 squared. So 5 squared, that's 25. 25 minus 9, so that's going to be 16. So we have 16 divided by 2 cubed. Added to, so 7 squared, that's 49. 49 minus 25, so that's going to be 24. So we have 24 divided by 2 raised to the power of 4 plus the rest of the terms. So let's name this as number 3. Now here, if we consider the second term onwards up to the infinite number of terms, this particular sum is going to be an arithmetico-geometric series. Here, if we consider the numerator of each term, so we have 8, then we have 16, then we have 24, and the rest of the terms. Clearly, these terms are going to be in arithmetic progression because they have a fixed common difference of 8. And also, we have 1 over 2 squared as the first term, 1 over 2 cubed, the second term, 1 over 2 raised to the power of 4 as the third term. So these terms are going to be in geometric progression with a common ratio equals to 1/2. Now, since this series is composed of an arithmetic progression and a geometric progression, we can say that it is an arithmetico-geometric series. Now what we will do, in the next step, we're going to multiply 3 with the common ratio of this geometric progression, which is 1 over 2. So that's going to give us 1 over 4 sum up to infinity. That will be equals to, now 1 squared over 2, that's the first term. When multiplied with 1 over 2, we're going to get 1 squared over 2 squared. Added to, second term 8 over 2 squared multiplied to 1/2 gives us 8 over 2 cubed. Added to 16 over 2 raised to the power of 4, and we have the rest of the terms. We're going to name this as number 4. Now what we will do, we will subtract 4 from number 3. Now on the left hand side, we're going to get 1 over 4 multiplied to sum of the infinite terms. This is going to be equals to 1 squared over 2. Added to, now 8 over 2 squared minus 1 squared over 2 squared, so that's simply 7 over 2 squared. Added to, next we have 16 over 2 cubed minus 8 over 2 cubed, so that's going to give us 8 over 2 cubed. Then we have 24 divided by 2 raised to the power of 4 minus 16 over 2 raised to the power of 4. So that's going to give us 8 over 2 raised to the power of 4. And we have the rest of the terms. So we can predict here that the next term is going to be 8 over 2 raised to the power of 5. So this is going to continue. Now here we have 1 over 4 times sum up to infinity. We have 1 over 2 added to 7 over 4. Now here, from the third term onwards, this sum is a geometric series, and it's an infinite geometric series with the first term a equals to 8 over 2 cube. So that simply equals to 1, and we have the common ratio r that will be equals to 1 over 2. So what we will do, we will find out the sum of the infinite terms of the geometric series. So that's given by a over 1 minus r. That means we have 1 divided by 1 minus 1 half, which gives us 2. So this entire sum is going to be equals to 2. So we now have 1 over 4 times sum of the infinity, that's equals to, we're going to sum the 3 terms on the right hand side. So this comes out to be 17 over 4. So that means the sum up to infinity, that will be equals to 17. So therefore, the sum to infinite terms of the infinite series, so this is going to be equals to 17.